Good day. So this is the second part of this lecture on cleaning and processing of the data. So last time I demonstrated some simple data cleaning strategies from the data that we used from the previous weeks. Now let's look at what can we do about this data. So just for a brief background review of the statistical tools that we already know and most of you have already done in doing, for example, their thesis in their grade 12. So we start with the simplest one, confidence interval. So confidence interval is basically the range of values for which the mean is basically it's the interval wherein the mean is within those interval. So the confidence interval for the mean is the range of values within which the population mean M is expected to lie with a certain probability. So for example, when you say the mean or rather for example the number of people in the Philippines, for example, that agree to a certain policy is we can say that with a confidence interval of 95%, the number of people who agree on a certain policy is say 95 to 98%. So basically it's the interval where you are sure that the population mean lies. So the confidence limit is the limits of the confidence interval. For example, when I say it's 95 to 98, so it's the limit is 95% to 98%. So basically the confidence interval is a range. So this is the calculation for a confidence interval if your population variance is known, or the other one if it's not known. The next one is hypothesis testing. So this is usually done, or rather it's because why do we do hypothesis testing? Because during experimental when we do sampling the experimental results, the results seldom agree exactly with the theoretical model. For example, in your model, the expected value is, for example, 14, but you got during your experiment, the course of your experiment, let's have a concrete one. For example, you are trying to measure the amount of the percent acidity, say, of vinegar. That is one of the experiments you did in chem lab before the pandemic. So for example, the value that you got is, say, 5%, or rather the known value is 5%. So that's according to the model that you it should be, so, or rather, for example, according to the label, it should be 5%. But in the course of your experiment, you measured it, and based on your calculations during your analysis, you got, say, 4.2%. So does that mean that does your result validate the model? Does it validate the actual percent vinegar? Did you get you get the correct one, or is the package lying? So you don't know. So this is where you apply hypothesis testing. So this is just an example. So do the results definitively support or it does not support the theoretical model? Because the model, for example, you know that it should be 5%, but you got 4.2%. So is that unacceptable? Is it near enough, or does this an evidence that the package is lying, or you got actually a wrong answer? Actually, on another side, you can view it as, can you, for example, since this is a laboratory class activity, can you argue to your professor that we got the correct answer? You shouldn't deduct our source, because according to our hypothesis with a certain interval, we actually got our evidence is close enough that it can support the correct answer. So for example, something like that, you can argue, and you can have statistically backed your results. So basically, those are some of the reason why you do hypothesis testing. So aside from that, you can also check it. So if it's too far, so you can check if you commit systematic or random errors that cause your result to deviate from what is expected. So basically, we have these different types of hypothesis tests, but we will just discuss most of the simplest ones that we use. So in hypothesis testing, we have a null hypothesis that postulates that the two or more observed quantities are the same. So for example, my results and the actual packaging are the same, so they are near enough that they represent the same means. Sorry, excuse me. And then we have the alternative hypothesis, which can be stated in several ways, so that depending if your test is single-tailed or two-tailed. So whether if it's single-tailed, you are checking if it's greater than or less than, or if it's a two-tailed test, so it's bidirectional. So that means the alternative is it's either too high or too low. So the significance level alpha is used to refer to a pre-chosen probability. So for example, the same with the confidence interval, you are sure with a 95% sure. So basically, you are not in statistics, you are not just going to say that I'm sure that this is statistically significant. So you should also quantify, since this is statistics is basically a mathematical tool. So there must be numbers. So you should be certain with a certain specific numerical certainty. So that's the significance level. So you are 95% sure, you are 90% sure, you are 99% sure. So that is your significance level. So that means also that based on your statistical test, you have a probability of getting an incorrect or getting it wrong. So the statistics can get it wrong with a chance of, say, for example, if it's a 95% significance level, that means there is a 5% chance that you might get it wrong. So so that's basically it. So calculated probability is the estimated probability of rejecting the null hypothesis. If P is less than the significance level, the null hypothesis is rejected. So you are just going to usually this is the one that is, if you are prone to reading journals, you will notice p-values. You will always notice p-values there. So for example, it's a calculated probability where the data is compared to your confidence interval. For example, you usually will see this in genetic testings, in in gene expression analysis, instead of, because that there are a lot of genes and values, so you have basically a lot of basically you cannot do t-test to all of them, so each of them are given the p-value. So basically the p-value is the shortcut. So you will say that if the p-value is less than the significance level, you reject your null hypothesis. So that means that is a significant result. So there is a significant difference. So basically that is because the null hypothesis always say that there is no significant difference. That's the thing with null hypothesis. We always say that there is no significant difference. But for example, in the experiment, you want to see if there is a difference between doing one experimental procedure versus another experimental procedure, and your null hypothesis always, the two experimental procedures are the same, so there should be no significant difference. But if there is a significant difference, you will see that if you calculated the p-value of the experimental method is less than your significance level. So if your significance level is 95%, so, or you can say it's actually 1 minus alpha, so that is 0.05. So if your p-value is less than 0.05, so that means if it's 0.03, so that means it's significant. You reject your null hypothesis, and that means there's a significant difference between the two results. So basically, that's the p-value. Now, you have heard of the z-test. So this is one of the hypothesis tests that we have. So the z-test is applied to populations. So if you have data on actual population, you use the z-test. So basically, that's that. And for the t-test, you have the data only for a sample. So you should remember what's the difference between a sample and a population. A population is basically the totality of all. whereas a t-test is just a small amount or a small portion of the population. So if you are using a small portion of the population, you're using sample data, you use t-test. If you are going to use population data, you use the z-test. So basically that's the main difference of the two. Now, since it's very seldom that we have actual population data, most of the time we only have sample data. So there are many different flavors of t-test. So we have t-test difference of means. This is just a simple two sample t-test. You are just going to test if the two population means are different. So this is one of the most common. And then we have the paired t-test. So this is open use when you compare two methods conducted on the same set of samples, where each sample is distinct from each other. So what's the difference between t-test for difference of means and paired t-test? So for example, let's say the population of male and female students in, say, Mapua. So Mapua, when I was a student in Mapua, the men there are more significantly more men than female. So let's say, for example, you want to test if the population of males and females students in Mapua are the same. So we used t-test for the difference of means. Now, when you are going to use t-test, for example, using the same idea, same setting. So in the Mapua, the males and the female students, you want to know if the performance of male students are the same with the academic performance of the female students. So for example, you are going to pull up their grade weighted average of the males and females. So you want to know if the weighted average of the males are the same with the weighted average of the females. So basically, that's the paired t-test. You have two different basically methods, in which case you have the males and the females, but they are being tested using the same sample, which is basically their academic performance. So do the males perform better than the females, or vice versa? So basically, that's where you use paired t-test. Okay, so that's the difference between the t-test for the difference of means, in which case this is just going to test if the population of men and female are do you have equal males and females now, male and female students in Mapua, versus the paired test, where do the males and the female perform the same academically. So that's when you are going to use the paired t-test. Now, we have comparison of variance, which is the F-test. So, F-test, basically when you talk about variance, it's basically how spread apart your data. So, for example, if you remember the bell curve in the statistics, the normal distribution, so the variance is a test whether your curve is skinny or flat. So, basically, that's a way how precise your sampling is. So, in doing the F-test, it's basically it's difference from sample means. So instead of getting the means, you are just the variance determines whether your for example, let's go back to the vinegar sample from a while ago. So we have 5%, according to the package, is 5%. Now you got 4.2% acid. Now the question here is let's say another group from your class got it as 4.1%. Another group is 5.3%, and then another one is 5.8%. So basically, the data in that experiment is spread about between 4 to 6, so around those ones. So plus minus 1%. That's the interval where the data is spread. And then another class in your one of your friends' class, in another laboratory class, so the same 5% acidity, the known acidity, and then the students there get the data that, for example, is 4.4, 4.6, 5.1, 5.2. So basically, it's plus minus 0.5. So you have different variances. So one class, they got a plus minus 1% from the actual value. Another class is plus minus 0.5%. So basically, you are going to test, as you can see, one class have more spread data than another class. So the other class has much the data that they got are more close to the true value versus the other class data. So basically, it's the variance. And in F, we want to know if the variance, does that mean that that one class performed better than the other class who got the plus minus 1%? So basically, that's basically you want to test if their variance are comparable. And then you have ANOVA. ANOVA is usually used if you have more than 2 samples, because paired t-test, f-test, you're just comparing two samples. But in ANOVA, you have, say, 5, 7, 8 samples. You want to detect difference in populations. And in ANOVA, it's analysis of variance. So they are basing variance to test if the two populations are different. And then lastly, we have the gross errors. Basically, this is a test for outlier. In actual utility, you first use the q-test, and then you check for the variance, and then you do the t-test. So I am discussing it in a reverse order, but q-test is one of the first tests that you should use. So this is a test if the data that you have is an outlier, whether you are going to include your data or not in your calculations. So why do you have to do that? Because sometimes let's say these are the data that are very problematic, and you commit a large amount of error in that data. So including that data in your actual calculation will destroy the rest of the analysis. It will compromise the rest of the analysis. So sometimes people remove the outlier. Although there are some debate among academics regarding the use of, or rather the removal of the outliers, because it might compromise the validity or the basically because in removing outliers, you are tailoring your data to fit a certain pre-planned parameter. Well, basically that's one of the arguments that they are talking about. But anyway, this is for removal of outliers, so use q-test. Okay, so that's for a review of statistics. So let's go back some other data processing tools in data science. So in data science, one of the ways to analyze data is through machine learning. And one popular machine learning method is conditional probability through naive Bayes. So basically this method aims to predict the likelihood that an event will occur given evidence defined in your data feature. So as we said before, since data science is focused if sometimes it's exploratory, at the same time it can be used to make predictions. So naive Bayes is actually a predictive method. So you will predict that this will occur given the evidence from the previous evidence that this has been happening. So for example, will you contract COVID if you go to the mall? So based on the previous data of the people that have gone to the mall, and say 50% have, after going to the mall, they contracted COVID. So basically, the naive Bayes will compute what's the will you get COVID as well when you go to the mall. So basically, that's actually a very simplified version, but something like that. So it's especially useful in using textual data. So this is mostly used in Google search engines. So we have several subtypes. Some multinomial naive Bayes, which describe discrete frequency counts of multiple variables. So it's going to detect how many times a certain word appears in a text or a certain document. So basically, it is just a basic count. So for example, you can have several keywords, and then it will count the number of keywords in that document. So it's a discrete frequency that this keyword 1 is 10 times, keyword 2 is basically those are the data it uses. Then we have the Bernoulli naive Bayes, describes the presence or absence of a nominal variable. So that means instead of multinomial naive Bayes, where you get 7 keywords, you can analyze a certain document for several keywords at once. For Bernoulli, only have one keyword, but it will calculate whether does that word appear how many times, or does it appear in page 1, page 2, page 3. So if it didn't appear in page 3, it will give you a value of 0. So basically it's a binary data, so it will give you yes, it appeared, no, it didn't appear. So that's Bernoulli. And then you have Gaussian. It combines the features of the Gaussian distribution. Basically, that's the normal distribution in statistics. And it's not recommended for text data, but it allows for positive and negative values. So it basically is a combination of the normal, you are applying normal distribution with naive Bayes application. And since the normal distribution deals continuous data, not categorical, it's not really good for doing it in text data, which is a categorical data. Now, other processing tools, we have correlations. Correlations usually done, these are some of the known correlations. We have Pearson's R correlation, which assumes that the data is normally distributed. So Pearson's R is used to determine whether are the two variables related. So for example, going to the mall and getting COVID. So does going to the mall cause COVID? Or are there any relationship that the opening of malls increases the cases of COVID? So basically, one variable is mall people going to the mall, and the second variable is getting COVID. So are they related? So does that mean that if the more people that go to the mall, the more cases of COVID we have? So that's one of the things that you can do in Pearson's R correlation. But there are some assumptions and limitations for Pearson's R, because it assumes that the data are normally distributed, the variables are continuous, and numeric and linearly related. And then we have Spearman's rank. This time it's for ordinal variables. So the limitations for this one is the ordinal variables that is related non-linearly and not normally distributed. So it for Spearman's rank, it converts numeric variable pairs into ranks by calculating the strength of the relationship between the variables and then ranking them per their correlation. So those are the two correlation analysis. And then Dimensionality reduction. So this is a pre-processing tool actually. So before you run data in a machine learning algorithm, you can you first use reduce the dimensions. So what are dimensions and why do we need to reduce them? So remember because the data in the big data that we usually use in data sciences have contain a lot of information and a lot of parameters. So let's say, for example, I believe you have done MATLAB exercises before. If you're going to plot something in MATLAB, you can have either a simple line, a simple number line, you can have a graph XY plane, or you can plot the data in a three-dimensional plot, so X, Y, and Z plane. So that means, for example, for a number line, you have one dimension. For for a Cartesian plane, you have two dimensions. And then the space or the XYZ planes, 3 dimensions. Now, what if you're dealing with 4, 5, 700 dimensions? So how can you actually make sense of your data? There are far too many. You cannot even plot anything that has more than, say, 4 dimensions unless you are using a time video that changes based on over time. For example, that's the 4th dimension that change over time. Say you cannot even plot a 5-dimensional parameter. Heck, it's very difficult to create a graph with the 4 dimensions because you need the graph to move over time, because the time series will be the 4th dimension. So anyway, the reducing dimensions is to make your you lose information in reducing dimensions, but it also highlights some correlations, some relationships in the data that normally you wouldn't see if you do not reduce dimensions. So these are and also it makes calculation easier. So we have several ways to reduce dimensionalities. You have single value decomposition, whereas your data you plot into a matrix and you decompose that matrix into 3 other matrix. So it's more common. It's actually a linear algebra. So, and then we have factor analysis. It compresses the dataset's information into a reduced set of meaningful, non-information redundant, meaningful inferred variables that underlie a dataset but are not directly observable. So, in factor analysis, you are, for example, dimension 1, 2, and 3 can be further compressed or say summarized in dimension A. So that's dimension A is your latent variable. So it assumes that your features are metric, continuous, and ordinal. The dataset have more than 100 observations and at least 5 observations per feature. So the sample is homogeneous, and the regression is 0.3 correlation between the features. So, and then the last one is principal component analysis. PCA is the one, the favorite tool used, especially in doing with biological data. For example, in microarray analysis, gene expression data, they use PCA. So, in PCA, you are just going to group data that are, basically, it's similar to a clustering, but not necessarily. So, it reduces data information to a set of principal components that are not information redundant. So, several data can be summarized at a single data, so something like that. So, it assumes variables should be continuous. Multivariate numerarity is preferred, but it is not required. And then, we have the regression methods. So, I believe you are familiar with the regression methods, especially you actually do that in their calculators, linear regression. So, it is used to quantify relations of one or several variables in a data set. So, it uses numerical data only and susceptible to outliers. No missing values must be done, and accuracy increases with dataset size. So, linear regression is the simplest one. So, if you are doing, say, in a chemistry laboratory activity, it's usually done when doing UV analysis, spectrophotometric analysis. You first get you first get your regression line of known values. So basically, you plot the absorption versus the concentration, and then you get a linear regression for that, and then so that you can get now the concentration of your unknown. So it's usually used in chemistry laboratory. So linear regression. So the more data that you have, the more known variables that you have, the better your regression analysis is. And then we have logistic regression. So this one is used to estimate values of categorical data. So linear versus logistic. Linear regression is numerical data. Logistic is categorical data. So categorical target variable based on selected features. So it does not really assume a linear relationship. And then we have ordinary least squares. So it's a statistical method that fits a linear regression line into your data set. And then we have clustering. So another processing tool. So clustering, we have either partitional or hierarchical. So when we say clustering, you cluster the data, you classify them into clusters. So it can be partitional. So you have you have only a single set of clusters. So for example, I can divide a class. So for example, the students in Mapua are, or rather say in your class. So I divided your class into groups. So that's clustering. And then you have hierarchical. Hierarchical clustering, you have basically a set of nested clusters. So for example, in Mapua, you want the pre-pandemic era, during parades or even during activities, they classify the students, for example, based on their department, and then within that department, based on the year, their student number year they enrolled. So basically that's hierarchical. So you separate it first on one parameter, then that can be further subdivided into subclusters and further subdivided into subclusters. So you have nested clusters. So you can visualize it with a dendrogram. So the dendrogram can be built as a top down or bottom up. So when we say top down, from the overall view, and then you further subdivide and subdivide and subdivide. Whereas the bottom-up approach of clustering is that you first have the most minimum cluster, and then you move up by joining similar clusters together, and then moving up again, join similar clusters together. So for example, during election period. So if the bottom up approach here is that you are assigned for each precinct during voting. Each precinct is situated in your certain school in the neighborhood or in a barangay. So the precinct, your barangay, and then within the barangay, so you form the district, and then each district is formed into your city, and then the city, if it's in Metro Manila, it becomes your NCR data. So that's the bottom up. So from the bottom going up, top down is from the top going down. So for example, the population in the Philippines, we divide it into per region, and then for each region per province, and then per province you have each province can further divided into, say, towns, pueblos, or cities, and then the cities can be divided into districts. So basically that's the top down, so from the highest level to the bottom level. Okay, so we have several clustering methods. You have k-means clustering. So this makes predictions based on a defined number of centroids present. So you have you let k be basically the number of centroids your data has. So you have a predetermined number of clusters that you want your data clustered into, and then the algorithm will cluster the values based on the distance of those centroids that you defined. So that's how that's k-means clustering. And then we have kernel density estimation. It's more of you can visualize it more of a graphical approach. So it's a density smoothing function. So it places a kernel on each data point, and then summing the kernels to generate a kernel density estimate of the overall region. So for example, here is your KDE clustering. Percentage of completion of primary school over basically in this method, you plot it into a scatter plot, and then if you use KDE, so you will smooth out the data points, and you will see here basically KDE will get the cluster based on how the densities. So you can see here cluster 1, 2, so several the dense datas or the dense clouds are your kernels. So aside from just getting the values of those kernels, you can also see here the density. So how many populations or how much of the data that you have in each cluster. So you can visualize it easily. So this KDE, you smooth it out and then look at the density, dense points with high density of the data in your graph or in your plot. So that's clustering methods. So those are some of the processing techniques we use to analyze, and as well as pre-processing tools prior to feeding these data into machine. So when you do, for example, when you have done dimensionality reduction, then you did clustering, and then this data now you can feed it to an algorithm for a machine learning algorithm to get the information you want. Okay, so machine learning will be discussed on the next module 3, but this marks the end of our module 2.